Today we're trying to use chemistry to identify cations in solution. As you can see on the screen, we have a body of water, a beautiful flowing stream, and we all know, don't we, that as we see a body of water, a flowing stream, river, lake, the ocean, we suspect that there are fish in that particular stream. I want you to come on a journey with me now as we think about fishing. I'm not a great fisherman, but I don't mind having a crack from time to time. But the key to fishing is knowing that the fish are there even though you can't see them. That's exactly the same when we think about ions in solution. You see, water contains all kinds of different dissolved ions in solution, and our task in HSC Chemistry is to see if we can use chemistry to draw those ions out of solution and prove chemically that they are in fact there, although we can't see them with the naked eye. So imagine you've got a body of water, a sample of water. Hidden within that water in HSC chemistry are one of 6 ions. Here they are appearing from the solution before our very eyes. Barium, lead, calcium, copper, iron 2 plus and iron 3 plus ions form the basis of our case study into ions in solution. Now we know they're there, but they are hidden from view. They're in the water, though we can't see them. And our task is to identify lead, barium, calcium, copper, iron 2 plus and iron 3 plus from solution. So using our analogy, using our fishing story, let's imagine that here are my 6 ions that I could possibly draw out from solution. And our task in chemistry is to use what's called precipitation reactions to cause these cations to combine with an anion, you can see it in the bait bucket there, and form what's called an insoluble precipitate. Ions on the left are soluble in solution, but if you give them the right anion, they will combine with that anion and form a solid which falls out, precipitates from solution. The precipitation, when you do your practical, is always seen as a cloudy substance, an actual physical solid particulate that will form in the solution, normally white in colour, we'll see some exceptions soon, and then slowly it tends to sink toward and settle on the bottom of your test tube or beaker. So we need to say, well, how could I, as a fisherman, using 3 types of bait in the bucket, chloride anion, sulfate anion, or hydroxide anion, how could I strategically use these in the correct order to capture one or more of my cation fish and positively identify it? Well, let's have a think about it. I could just choose any particular piece of bait at random. So let's say I'm just a fisherman like I tend to be. I just stick a prawn on the hook, chuck it out and hope for the best. That's not a good way to approach this chemistry. We're going to see that the order of anions is vitally important. And the reason is that if you put hydroxide on the hook first, we're going to see that it's not the best bait for selecting individual cation fish because more than one fish is interested in the bait. We can see here on the slide that lead will combine with hydroxide, but likewise iron 2 plus, iron 3 plus, and even copper ions will combine with hydroxide ions to form their respective precipitates. Our task is not simply bucket fishing, bucket chemistry, drag them all out of solution. Our task is to drag them out in an order which shows us exactly which cation is which. So we better put that bait back in the bucket and we'll put those fish back in our solution. A much better choice to start with when any one of these 6 ions is possible is to put the chloride ion in first. The reason we use chloride is that it is highly soluble. Hardly any cations will react with chloride to form an insoluble precipitate. In fact, of all our 6 fish that are possibilities, they all here can see that chloride's in solution, but only one of them is dumb enough to fall for chloride. All the other fish can realise that chloride isn't really the kind of bait that's going to drag them out of solution. But poor old lead can't resist chloride. Lead ions are highly precipitative. They react with almost anything. In fact, they're going to react with everything in the bucket, hydroxide, sulfate, and even chloride. So in order to eliminate lead, we have to test with chloride first. Chloride is selective enough that only lead will precipitate and lead will be dragged out of the solution as lead chloride. Let's take a look at the chemistry. Lead ions, lead 2 plus aqueous ions, you can see they're aqueous on the left, will combine with 2 chloride ions, aqueous in solution, to form lead chloride solid. Notice the S indicates the solid state, which of course is the precipitate. Having successfully removed lead as a possibility in solution, you can now say as a chemist, if you added chloride ions to a solution which potentially contained any one of these 6 ions, if you got a white precipitate, it would have to be lead chloride. Lead is the only ion that would precipitate with chloride. So we've eliminated 1 and we've got 5 left, but we've only got 2 types of bait left in the bucket. Our question is hydroxide or sulfate. Well, we're going to select sulfate because sulfate is the next most selective. We see here all the fish know it's there, but calcium falls for it. Calcium can't resist sulfate. Calcium does react with sulfate in solution. But frustratingly for us as a fisherman, here comes barium as well. Barium and calcium, sitting very close together on the periodic table, both have similar reactivities with sulfate and they both form precipitates. So sulfate will, in the absence of lead, drag calcium and barium out of solution as well. Let's take a look at the chemistry. Here's my barium fish and my calcium fish. They both react with sulfate in the following way. Barium and calcium ions react in the presence of sulfate aqueous ions to form solid precipitates, barium sulfate and calcium sulfate. Frustratingly for us as chemists, not only do they both form precipitates, but the precipitates look exactly the same. Both of these solid precipitates fall out of solution as a fine white precipitate. This will settle on the bottom of the test tube. So when we're trying to distinguish between these 2 ions, barium and calcium, adding sulfate can show us that they are present, but it can't distinguish between barium and calcium. We need a follow-up secondary test. Luckily for us, we have one. If we bring our barium ions down here, and we brought out the Bunsen burners, we can now conduct what's called a flame test on these solutions. So let's think about our story so far. We've eradicated lead as a possibility by adding chloride, and we've taken lead out of the situation. Now we've tested using sulfate and we have got a positive test for the presence of calcium and or barium. Both of them are white precipitates, so we know that calcium and or barium is present, but we don't know which one. If we take that same solution that contains the barium and the calcium or the calcium ions, and we spray carefully 3-4 mils of a fine mist of that solution into the flame in the laboratory, we'll start to get different coloured flames. The calcium ions will absorb heat from the Bunsen flame. The electrons in the electron shell will become excited, they absorb energy, but then the energy that they've absorbed they will also release as the electrons fall back down toward what we call a ground state. And that energy, the wavelengths of light that are emitted as those electrons fall back down, are visible to us in the red area of the colour spectrum. So calcium ions release a red colour when they are exposed in solution to a flame. Barium ions conveniently release a green colour spectrum. Not so convenient if you're red-green colour blind. However, this is our follow-up distinguishing test. We can now see that if we get a positive with sulfate in solution, we can conclude that barium or calcium, or maybe both, are present. If we aspirate that solution into the flame and we get a red colour, we can conclude that we have calcium ions. If we get a green colour, we can conclude that we have barium ions. So now, having eradicated those 3 ions from solution, sequentially by adding chloride and then sulfate, exposing them to flame tests, we're now back to our last 3 ions. We've only got one piece of bait left in the bucket, hydroxide. All 3 of our fish are interested. Copper falls first, iron 2+ next, and iron 3+ next. In other words, all 3 of these ions will react with hydroxide in solution to form a precipitate. Let's take a look. They get pulled out of solution and the chemistry is as follows. Up the top, copper ions will react with hydroxide ions. See, on the left they are aqueous, but on the right they have formed a solid. And they form this time a precipitate with a unique colour. Copper hydroxide is blue. Now, iron hydroxide is a lighter green. It tends toward white, but it has a pale green hint about it. Iron 2 hydroxide is green. Iron 3 hydroxide down the bottom forms a nasty brown colour. So even though all 3 of these cations in solution, copper, iron 2 and iron 3+, react with the same anion, hydroxide, we are able to distinguish between them as chemists by looking at the colour of the precipitate. Blue for copper, pale white-green for iron 2, and browner for iron 3, a brown precipitate. A couple more comments at this point, however, is copper does give us the luxury of a further distinguishing test, and we can again expose the solution. If we got a blue precipitate, we could further distinguish the presence of copper 2 plus ions in a flame test as described before, and copper ions go a blue-green in solution. We talk about barium as having an apple green colour, and the copper ions would go blue-green. So you could, just as a follow-up test, take a small sample of the solution that you had got a positive for copper hydroxide with, take some of that filtrate, expose it to a flame test, spray it in a fine mist, and if you've got a blue-green colour, that's further confirmation for the presence of copper ions. You do need to know that colour. Iron 2 and iron 3 don't have a colour for a flame test that we need to know. However, there is one last anomaly we need to note about iron 2, the second precipitate on the screen. If you give iron 2 enough time, I'll just put a clock there, if you leave your iron 2 hydroxide exposed to oxygen, which you do when you draw it out of solution, over time it starts to turn brown. This is not an indication that iron 2 was present in solution originally. It's just that iron 2 is steadily reacting with the oxygen, it's oxidizing and forming iron 3 plus. So you need to be careful. If you're told, or if you see for yourself, that you get a strong positive in the presence of hydroxide, it's a white precipitate with a greenish hint about it, you would correctly conclude it's iron 2 plus. However, if you came back 10 minutes later and you looked at that same result and you said, hang on, it's brown, maybe I got that wrong. No, you didn't get it wrong. It's just that it has steadily oxidized to iron 3, and now the iron 2 plus has become iron 3. So you just got to be careful that you check it early enough and you record your results straight away. So we've seen now the importance of the order that we test for these solutions. We have to eradicate lead before we then eradicate barium and calcium, and then we're free to add the hydroxide to test for the final 3 ions. If you don't get the order correct, you risk a false positive. For example, if you didn't eradicate the possibility of lead ions first, because lead is so precipitative, if you went and added sulfate to solution and you hadn't ruled out the possibility of lead, you would get, if lead was there, a lead sulfate precipitate, which is inconveniently white and looks just like barium and calcium. And without a flame test for lead, due to toxicity risks, you wouldn't be able to tell the difference between lead, copper, or lead, barium, or calcium, and you wouldn't be able to distinguish between them. Let's have a look at a real example of an HSC question now. Here's a question from 2013. It was worth 5 marks just on this theory of cations. You can see that we're told some information. A solution contains 3 cations, barium, copper, and lead. The flowchart indicates the plan used to confirm the identity of these cations. We have a quick look at the flowchart and you can see that the solution in the first instance has hydrochloric acid added to it. It's filtered and there is a precipitate. The filtrate, that's the solution left behind that went through the filter paper, is then added H2SO4, sulfuric acid is added to that filtrate, and you get a filtration happening again. There's a precipitate that did come from the addition of sulfate ions, and that's isolated, and then you end up with a solution filtrate 2 with still an invisible cation, an invisible fish sitting in it that hasn't been identified. And we're asked to name precipitate 2. We're looking to be able to identify precipitate 2 for 1 mark. Well, let's have a look at what's actually happening here. Firstly, the solution that contained all 3 ions, we're told, had chloride ions added to it. If you think about our fishing trip, this is good chemistry. We're adding chloride first because we wish to eradicate the possibility of a certain type of fish. What was that fish? It was the lead ion fish. This is the fish that can't resist any kind of bait. We're going to get rid of that fish first. The fact that we got a precipitate when we added chloride is a positive for the presence of lead. Lead chloride precipitated out. So we can now conclusively say precipitate 1 is lead chloride. It's now gone from solution. They've filtered the solution, and here's the remaining clear solution with 2 more hidden fish. But what did they do to this solution? They then added more bait. sulfate 2-. If you went back to our theory, you'd remember you add sulfate second to try and draw out barium and or calcium. Obviously in our solution, barium's the only possibility. So when they filtered off the precipitate 2 must have been barium sulfate. It's the only one of these ions, once lead's been eradicated, that will react with sulfate in solution. So we can now name precipitate 2 as barium sulfate. Part B of the question says, write a balanced net ionic equation for the formation of precipitate 1. So we're going back here to precipitate 1 and we want to show how lead chloride formed. It was precipitate 1 because chloride was added to a solution and a positive precipitate reaction occurred. So how would we write that? Well, we want to write our lead ions in aqueous form, lead 2 plus aqueous, it's in solution, plus we added to it chloride ions from the HCl, and we formed lead chloride, PbCl2. The 2 chlorines are required to balance out, because they're worth 1- each, the 2 positives associated with the lead ion. Now, note, we must balance it. If I had 2 chlorides required on the right, I must have had 2 chlorides on the left. That will get you your mark for the precipitate 1 in the question. There's a final part to this question that we'll look at now. It says, suggest a test and the expected result that would confirm the identity of the metal cation remaining in filtrate 2. So we need a test and the result we would expect from that test to confirm the identity of the metal cation. So we're talking about filtrate 2 here, where this arrow is pointing to. Of course, in our discussion so far, we've eradicated lead by adding chloride. We've eradicated barium by adding sulfate. So we know, don't we, that the final ion in solution is copper. However, it's important that we don't just use a series of elimination to prove the presence of something in chemistry. We actually need to use a chemistry test to show that it's there. We can't just in this question say, well, because the other 2 were positively identified, the third one must be copper. That's not good science. We now need to show that copper is there using good chemistry. So let's describe a test. We've used sulfate, we've used chloride, we've dragged 2 ions out. So we describe a test in the following way. The addition of excess sodium hydroxide, I'm using the idea of excess and excess from the question. It's always good to replicate the information the HSC has given you. The addition of excess sodium hydroxide, there it is, the hydroxide ion, to filtrate 2, this is my final solution with the hidden ion in it, would result in the formation of a blue precipitate, copper hydroxide. The test is the addition of excess sodium hydroxide. The expected result is the formation of a blue precipitate. Now that would get you your 2 marks, but in chemistry, you can never underestimate the power of an equation. If you accidentally made a mistake, you misnamed the colour of the precipitate, you forgot to mention it, if you put an equation in here, the equation tells you everything that the examiner wants. Copper ions plus hydroxide ions gives a solid copper hydroxide. It backs up your work. Now that would get you 2 marks, however some of you are probably thinking there's another test I could have done. And so I'll mention that here as well, but you would not need to mention both tests to get the 2 marks here. You could, of course, expose the final solution to a flame and observe the colour for a flame test. A small amount, it's always good to suggest an amount, 3 ml. Of filtrate, you could have said 2 ml, 1 ml, a fine mist. You want to suggest an amount wherever possible when describing tests. A small amount, 3 ml of filtrate, could be aspirated in a flame of a Bunsen burner. The appearance of a blue-green flame would confirm the presence of copper 2+. The test is the flame test. You've named the test and you've given the expected result. You've demonstrated your understanding that a unique blue-green flame colour would result if copper ions were present. So here's a way to think through how we can positively identify cations in solution. The order is vitally important. Knowing how to represent each with a chemical equation is vitally important. And if you're ever going to be given a mark for correctly identifying the states, this is where you'll get it. Did you notice in the previous slide that part B here was worth 2 marks for a balanced equation for the formation of precipitate 1? If you didn't put your states in correctly here, you would not get that 2nd mark. I hope you found the fishing story helpful. Good luck as you identify ions in solution.